So what about L1 regularization, right? So again we can write it here again, right? So we have less than equal, so L1 norm is less than equal to epsilon, right? And why this is important is, let's look at just for, let's say, theta 1, right? So L1 norm of theta 1 would be something like this, and there's a non-differentiable point here, right? So we have multiple subgradients here, like this and this and this, all this family of subgradients, everything which is below this area in this range, right? So basically we have a subgradient at 0, right? Now let's plot the function again. We have something like this, right? And if we plot this regularization, right, we'll have something like this, depending on epsilon, but yeah. Right, so we have this green constraint space, and what happens is, at every of these corners we have so many tangents, right? Here also. So what happens was, because of this thing, where in the Lagrangian form, where the tangent is shared between the actual function you're trying to optimize and the constraint, right? So it's much easier for these edge points here, let's change the color. So it's much easier for these edge points in red to find a shared tangent with the actual function we are trying to optimize, in comparison to these edges, right? Because there's a unique gradient at these edges, and the chances of having a shared tangent with the actual function is much lower than at these 4 red points I've circled, right? So that's one of the reasons why L1 produces sparsity, because at any of the axes only one of the terms here is non-zero, right? So yeah, so in high dimension it's more extreme. So basically what we're trying to say is that the edges are highly likely to intersect with a shared tangent with the actual function we're trying to optimize, and that's why L1 normalization basically works and promotes sparsity and feature selection.